All right, so this idea of solving two systems of equations with two unknowns can be expanded to three and four systems of four equations and four unknowns. We're going to go ahead and look at solving a system of three equations and three unknowns. So there's different possibilities that can happen with equation of three variables. It's going to be represented as a plane in three dimensions. So think of them as like pieces of paper that go on forever in each direction, kind of like a line. So there's some different possibilities that can occur with it. We're going to go ahead and look at this system of equations. And the idea is it's very similar to solving a system of two equations and two unknowns. You're going to eliminate one of the variables, and I'll go ahead and label these three equations 1, 2, and 3. And so we're going to eliminate one of the variables. So what's different here is I got three equations, and I want to eliminate one of the variables twice in two different combinations of the equations. And I'm looking for the same thing. I'm looking for opposite signs like a plus and a minus. If there's not one there, then we'll have to multiply by a negative to get what we want. So I look at the x's, they're all positives. I look at the y's, they're all positives. But I do look at the z's. There's a positive z and a negative z in equations 2 and 3. So I think what I want to do is I want to go ahead and add those two, and that's what we're going to do first, is we're going to take equations 2 and 3, and we're going to go ahead and add them just like we do with a system of two equations and two unknowns. And we're just going to add straight down, add the variables together, add the numbers together on the right-hand side. And I have a hard time drawing these z's with this stylus here. Okay, so that's our equation. We add the x's, we get 3x. We add the y's, we get 2y. The z's are going to cancel when we add, and 2 and 2 is going to make 4. No relation to this being 4, but we'll go ahead and call this equation 4, just so we can easily refer to it. And now what we got to do is, I've used equations 2 and 3. I probably want to use equation 2 because the z has an opposite sign of the z in equation 3 and the z in equation 1. They're both positive in 1 and 3. So what I want to do is I want to make the z's have the same coefficient of 6. So what I'm going to do is we're going to take that equation 2 and we're going to multiply everything by 6. And we'll go ahead and do that right here. So I'm going to write equation 1. And then we'll go ahead and write equation 2. And if you write it like this, it's real easy to kind of follow what you're doing. And what I want to do is I want to multiply that second equation by 6. So then I'll have a 6z and a negative 6z for when they drop, when they cancel out. So anything you do to the one side, you got to do the other. So rewrite the top equation again. And now we multiply that second equation by 6. So 12x plus 6y minus 6z is equal to 12. And we'll go ahead and add down. So 15x plus 15y, the z's drop out, equals 15. And we'll go ahead and call this equation 5. Now what we've done is we've reduced it down to a system of two equations and two unknowns with equations 4 and 5. And it's the same procedure as before. So the one extra step there is breaking it down into two equations and two unknowns by eliminating one of the variables twice. Alright, so now I look at the x's and the y's. They're all positive, so I don't have a positive and a negative. And what I'm going to do is I'm going to look at the greatest common factors of the coefficients. So I look at 3 and 15. Sorry, I think I said greatest common factor. I meant to say least common multiple. Least common multiple. So looking at the least common multiple, 3 and 15. And that least common multiple is 15. 15 goes into 15 and 3 goes into 15. I look at the y's and I have 2 and 15. So greatest common factor there, since 2 and 15 are what's called relatively prime, which means 2 is just 2. 15 is 3 and 5. They don't share any primes in common. their greatest, or not their greatest, their least common multiple of 2 and 15 is going to be 30. So I'm going to deal with the smaller number. I'm going to go ahead and take care of the x. So we're going to write those two equations, 4 and 5. And we're going to eliminate the x because it deals with a little bit smaller numbers. Another reason for doing the x's is if I want to eliminate the y's, I need to make them both look like 30. So I'm going to have to multiply both equations by something in order to get them to be a 30 and a negative 30 so that they'll drop out. So we're trying to go for a path of least resistance, least amount of work. If we take that top equation, if I multiply it by negative 5, the 3 and the negative 5 will make a negative 15. So that's what we're going to do with equation 4, is we're going to multiply it by negative 5. Again, we're going to draw ourselves an arrow just to indicate what we're doing. And we have negative 15x minus 10y equals negative 20. Don't forget to multiply that other side. And then we'll write that other equation right underneath. And then we'll go ahead and add straight down. So you see that the x's cancel out. Negative 10y plus 15y is 5y. And negative 20 plus 15 is negative 5. So we're going to go ahead and we're going to divide both sides by 5, and we'll get y is equal to negative 1. Okay, now we have a system of two equations with 4 and 5. So like we've done before, we're going to take one of the equations and we're going to substitute in y equals negative 1 into one of them. I'm looking at the numbers, and well, it looks like 4 has smaller numbers, so I think I'm going to use 4, and I'm going to substitute negative 1 in. So I'm going to write equation 4. And this time I'm going to be a little bit lazy. I'm going to go ahead and plug in the negative 1 in there. But I did write equation 4 there just so I know what I'm doing, because it turns into a big mess if you're not careful. So I did write down that I'm doing equation number 4, and we're going to plug negative 1 in for the y. And then what happened is we had 2 times negative 1, so that's going to be a negative 2, and then we add 2 to both sides. So when we add 2 to the 4, that becomes a 6. And then what we're going to do is we're going to divide both sides by 3, and we should get x is 2. Okay. Alright, now we've got 2 of them, then the process pretty much unravels. We pretty much get the rest of them. Now I have options. I can plug in x and y into equations 1, 2, or 3 and solve for the remaining variable, which is the z here. And then again, we're trying to go for path of least resistance. And so we'll go ahead and equation 3 looks the easiest. So I'm going to go ahead and write down equation 3. X plus y plus z is 2. I'm going to replace the x with a 2, the y with the negative 1, and then we have the z there. Okay. So 2 plus 1 is, or I'm sorry, 2 plus negative 1 is 1. So we're going to subtract 1 from both sides, and we get z is equal to 1. And we'll go ahead and write our point of intersection as x, y, z, 2, negative 1, 1.